Let's talk about the tiny powerhouse you carry around with you every single day, your smartphone's battery. We're going to pull back the curtain and explore its secret life.
On the surface, it seems pretty simple, right? You plug it in, it charges up, you unplug it, and it just works. But inside that slim little case, there's an incredible whirlwind of complex chemistry and precision engineering going on. So what is really happening in there?
Well, it all boils down to something called the rocking chair mechanism. And the hero of this whole story is the tiny lithium-ion. Just picture these ions as little energy carriers constantly rocking back and forth between 2 points to either drop off or pick up a charge.
Okay, let's follow one on its daily dance. When you're scrolling through your phone, that lithium-ion travels from a negative side, the anode, over to a positive side, the cathode. That journey releases an electron, and it's the flow of billions of these electrons that actually powers your screen. Then, when you plug your phone in, the charger provides the energy to push that ion right back to the anode, getting it ready for the next day.
But where does all this happen? I mean, what does the dance floor look like? To get that, we need to crack open the case and look at the physical stage, the internal architecture of the battery itself.
So every lithium-ion battery has 4 absolutely critical parts. We've already met the cathode and the anode, the start and end points for our little ion. Now the highway that it travels on is a liquid called the electrolyte. And maybe most importantly, there's the separator. It's this super thin wall that keeps the anode and cathode from touching. Because if they did, game over. That's a short circuit. All 4 of these have to work together in perfect harmony.
Now, let's zoom in on the anode, because this is where things get really interesting. For years, it was made of good old reliable graphite. It works, it's stable. But the future is silicon carbon. Look at that jump in capacity. We're talking over 10 times more energy storage. But here's the catch, and it's a big one. When silicon is full of lithium ions, it swells up to 4 times its original size. Learning how to manage that expansion is one of the single biggest challenges in battery engineering today.
You know, it's not just about what it's made of, but how you put it all together. The old school method was the jelly roll, where you just wind all the layers up. Think of it like a long, inefficient country road. But the modern way is Z-stacking, which is more like a perfectly planned city grid, and it's better in basically every single way. Less resistance, which means less heat, more even temperatures, and it's way, way more space efficient.
And what does that mean in the real world? Well, check this out. Just by switching from that jelly roll to a stack design, engineers can cram about 5% more energy into the exact same physical space. Now, 5% might not sound like a lot, but in the world of smartphones where every single millimeter counts, trust me, that is a huge win.
Okay, so we've got the chemistry and we've got the physical structure, but none of that works without something smart keeping it all safe and running efficiently. So now, let's meet the brains of the operation.
This right here is the Battery Management System, or BMS. It's a tiny little circuit board, but it is the absolute unsung hero of your phone. Think of it as a guardian, 24/7, constantly watching the voltage, the current, the temperature, everything, to make sure that battery stays within its safe operating limits.
Ever wonder how your phone actually knows it's at, say, 73%? Well, that's the BMS using some incredibly clever math. The old way was called Coulomb counting. Think of it like a simple accountant, just ticking off every bit of energy that goes in and out. It's okay, but tiny errors add up. Modern phones use something much smarter, Kalman filters. This is more like a smart weather forecaster. It builds a model to predict the battery level, and then it constantly corrects that prediction using real-time data. The result is way more accuracy over the long haul.
The BMS is also the magic behind features like optimized charging. See, it turns out that leaving a battery sitting at 100% for hours and hours, like overnight, actually stresses it out and makes it age faster. So your phone learns your routine. It'll charge up to 80% pretty fast, and then it just waits. It tops off that last 20% right before it expects you to wake up and unplug it. It's a brilliant little software trick that really does extend your battery's overall lifespan. And that brings us to a really important topic. I mean, these batteries are packing an unbelievable amount of energy into a tiny space. So what happens when things go wrong? And more importantly, what's built in to prevent disaster?
The ultimate failure mode for a battery is something called thermal runaway. This is the nightmare scenario you've probably seen videos of. It's a terrifying chain reaction where the internal temperature starts to rise, and that heat creates more heat, feeding itself until the battery fails, often catastrophically.
So how does that terrifying cascade happen? Well, it's a step-by-step process. Around 80 degrees Celsius, a critical protective film on the anode starts to break down. If the heat keeps climbing to 130 degrees, that all-important separator melts, causing a massive internal short circuit. Then, if it hits 200 degrees, the cathode itself starts to decompose, releasing pure oxygen, which is basically fuel for a fire. Now, the key thing to remember is that every safety system in the battery is designed to stop this process before it gets to the next step.
And if the software controls fail, there are actual physical fail-safes built right into the battery cell. There's something called a PTC resistor that acts like a choke, basically squeezing off the flow of current if things get too hot. There's also a current interrupt device, or CID, which is a tiny pressure switch that physically and permanently breaks the circuit if the pressure inside builds up. And if all else fails, there are safety vents designed to pop open and release that gas in a controlled way, preventing an explosion.
But even with all those amazing protections, there's one simple, unavoidable fact. And this quote says it perfectly. Batteries are consumables. From the very first time you charge it, a slow, irreversible process of chemical aging begins. Every single cycle just wears it out a tiny, tiny bit. So, knowing all of that, where is this technology going? Let's take a look at what the future holds for the power in your pocket and what it means for the planet.
Well, that future we talked about with silicon-carbon anodes, it's not the future anymore. It's already here. Flagship phones are now shipping with this tech, enabling absolutely massive battery capacities without making the phones feel like bricks. We're seeing power reserves that would have been pure science fiction just a few years ago.
But what about lifespan? Well, the industry benchmark is pretty consistent. Most phone batteries are designed to hold on to about 80% of their original juice after 500 full charge cycles. For most of us, that works out to about 2 years of use before you really start to feel that degradation.
And of course, that leads us to the elephant in the room. With billions of these devices on the planet, the environmental impact is just staggering. 50 million tons of e-waste every year is a number that's almost impossible to wrap your head around, and batteries are a particularly nasty part of that problem. But there is a very powerful solution: recycling. Just look at these numbers. Compared to mining new materials from the earth, recycling old batteries uses dramatically less water, way less energy, and produces far, far fewer carbon emissions. It's just undeniable. This isn't just a nice thing to do, it's an environmental necessity.
And the key to making this whole process work is a substance with a pretty cool name: black mass. When old batteries are safely shredded, you get this black powder that's incredibly rich in all the valuable stuff: the cobalt, the nickel, the lithium. This black mass can then be refined to recover those critical metals so they can be used to build brand new batteries. It's how we close the loop.
So, you see, from the atomic dance of a single lithium-ion all the way up to the global logistics of recycling, the battery in your pocket is a true marvel. It's this perfect synergy of material science, electrical engineering, and brilliant software, all working together. Which really just leaves us with one last big question. What will we demand of this tiny powerhouse next?